Okay, today we're going to be working on finally getting back onto this mill fixture, and we're going to be working on this end support here for the bearings, to support the bearings on the opposite end of the rotary table that mounts over here. So I just opened this up to give you an idea of what this piece looks like. So let's jump over to the CAM software. I actually already program this because it's really of no use for me to show you how to run this software, because the chances are that people watching these videos aren't going to have this software, and so I can go through all that trouble, but it's really unless you have this Esprit software, which is pretty expensive, it's not going to do you much good. But I can show you the simulation of what's going to happen here. That might be worth watching. It's going to mill the slot, then we're going to drill these two bigger holes for the tie down bolts, and drill and tap 2 1/4 holes in the middle. Right now in the machine the stock looks like this rectangular shape piece in the simulation. So that's all we're going to do on this today. Just a simple program. Because it's so simple, I can put in a little explanation of a few other things in this video that might be helpful for somebody. Process code here, which I think I've selected the right thing for this little Haas machine, and I'm going to then open the code. Let's see where I put it here. Okay. I'm going to open the code in this software, this Predator software I use to transfer it to the machine, and also we can see it a little nicer in this software. It's the same software I used for the explanation of the code on the lathe, but the milling code is slightly different. So we're going to look at that, which is here. Just for a quick explanation of the code on the milling machine. And this is a real short, simple program, so this shouldn't take too long, so kind of bear with me on this. The percent sign at the top of every program, actually all programs begin and end with a percent sign. That's just to show the control where to start. The program starts and ends for the purpose of uploading it to the machine as well as to run the program. Now all programs are required to have an O name to the program. This case I'm calling it 0 because a Haas will take a 0 program into it. Some machines this might give you an alarm, or you might have to have at least 4 digits in this name. I think a Finut control requires that, and it might not even receive a 0. You might have to have it like that, a 0001 for program 1 in the control. This name is how the control keeps track of the program in the control. It's kind of like the name of a file in a folder, if you will. So when you look at the menu in the machine, you'll see this name, and then you'll also see this description, which is in parentheses on display in the machine, the description of the program. Everything in a G-code program that's in parentheses like this is ignored by the control of the machine. It's only for your purposes, so that you can put notes in the program like this note here. This end sequence number, I have the post processor putting it in to match the tool number that I'm looking for. So if you have to restart the program for any reason, it's easier to search down it if you have end sequence numbers. And if I'm using, say, tool 1, in this case, more than once in the program, I might even put the next time I use it as N1.2 like that, so that I can search down for this N1.2 and it'll give me the second use of that tool. Because if you just search tool 1, you're going to have to search twice, tool 1 and then again for tool 1 if it's used more than once in the program. So that's usually what I do. The controls allow you to put decimal points on the end sequence numbers. Most controls do. Okay, this line of code is basically a preparatory line of code that you put excuse me, you put in between or at the beginning of tool changes or the beginning of the program. which is a rapid move, is a GOO, and G90 is absolute positioning mode. G40 is the cancel of cutter compensation, and G17 is the plane of compensation or circular interpolation, as the G17 plane is the XY plane. G90 again here, it really isn't needed, but it's again redundant command. G54, because G90 is a modal command actually, so unless you change it, it carries on through the program. Is the reason it's not necessary here really, again, unless you were changing it. G54 is the fixture offset we're using. Rapid again, GOO to this X and Y. And the A axis is not being used here, so this is not needed, but it doesn't hurt if the A axis is mounted on the machine. Otherwise this will give you an alarm if no A axis was there, but it's already mounted on this machine. Okay, G43 is calling for a height offset of a tool. In this case, tool 1, HO1 is tool 1, and DO1 is the diameter of tool 1. Haas control uses diameter on its offset pages, but if the machine used radius on its offset page, this D command would still be the same in the program. It's just your offset page would be different. You would use radius instead of diameter. The Mitsubishi mill that I have at the bigger shop uses radius for its tool offsets, but the command here on this line is the same. And then we're wrapping into 1 inch in Z. Turning the spindle on to 3000 RPM in the forward direction, MO3. Dwelling, GO4 is a dwell for 2 seconds. If you're turning coolant on or something, this allows the coolant to get on the tool before it gets down into the work. I have no coolant on command here. I probably will put it in here. The post processor must need that revision or alteration to put it in. I guess it's not putting it in there. And then we're going down to Z minus 1/8 of an inch. This is going straight down off the stock, so it's not hitting anything, so it's not going to be a problem, even though it's doing it at rapid, because you see there's no feed rate called out yet. You can tell this line. So GO1 is a linear feeding move at this feed rate, and G41 is calling for left-hand cutter compensation. It's going to move over to this X.3075. This is just the roughing passes for this keyway, which is a 5/8 wide keyway. So that's why that's a little bit less than 0.3125. And then we're feeding to Y 1 inch. And then this Y minus 1. Because I added an increased clearance move here, it actually is feeding from this Y of 1.325 to the 1 inch, just so the cutter won't hit the stock. That's the way the CAM software puts it in there. So this could be all one line from this Y to this Y in reality. So these two Y's aren't really necessary, but this is the way the software puts it in there. Okay, then it ultimately gets to this Y minus here, and then it's canceling cutter compensation and moving back to the same X, you'll notice as was up here. I can go into a more explanation of cutter compensation and why you apply it on certain lines and take it away. I wasn't going to do that in this video because that's a more time-consuming explanation, and so that'll be for another video. Okay, we're wrapping back up to Z 30 thousandths, and then we're moving up to this Y and so on, and it's taking these passes down to rough the key slot out that we're putting in the middle of the part there. So that's basically what it's doing here until we get to there is a finish, kind of a finish pass of this where it's actually going, see here, it's going to the 312.3125 here, and here, and those are the finish passes of the key slot. So you'll notice that these are actually at the dimensions of the key slot width irrespective of the diameter of the cutter. That's the advantage of using cutter compensation, is you actually program the actual shape of the part in this case to do that. And like I say, I'll explain that in another video more in more detail, and it'll make better sense. So then we're going to change to tool number 2. MO6 is a tool change, tool 2, and it's calling G54 again, and this is where it's drilling those 2 holes. The first one starts at X 4 inches and Y 0. This A is again because the A is on the machine. And this is calling the offset again, the height offset of tool number 2. The diameter is not necessary for a drilling cycle because a drill doesn't use cutter compensation, so but the software puts it in there regardless of if it's a drill or an end mill. Coming to 1 inch, turning the spindle on at 1500 and in the forward direction, dwelling for 2 seconds. That's everything the same as last time, more or less. Okay, G98 in front of a drilling cycle. This G83 is a drilling cycle, is a which is a PEC drilling cycle. Actually, G83 is telling the machine to come up to this 1 inch where it starts the drilling cycle. Really, it's starting the drilling cycle at 1 inch here for a clearance, and it's coming down to this R value of where it starts the feed rate above the part. So when you put a G98 in the program in front of the G83, it'll always retract between the holes to 1 inch in Z on a what a lot of people refer to as a can drilling cycle, or a drilling macro really is a more accurate term for this. If you wanted to only retract to this R plane between drill holes, you would have a G99 here instead of a G98. And then the other hole is at -4 inches. You don't need a Y because the Y, it doesn't change. It just moves over to 4 inches. And then you wrap it up again, in this case to the 1 inch, and you cancel. A G80 is a cancellation of all of these drilling, boring, threading, tapping or whatever cycles. G80 cancels them. Otherwise, any movement, if you didn't cancel this drilling cycle, any movement the machine makes in the X and Y plane, it's going to try to drill this hole in, so you have to cancel it if you don't want it to do that. In this case, it's just turning the coolant off here, MO9, and coming straight up in Z and turning the spindle off. And then this is an optional stop, just like this is. I didn't explain that, but this optional stop turns off the, stops the machine. Doesn't turn it off, but it stops it at the, if the optional stop button is enabled or key is enabled on the control. And change to tool 3. And this is basically the same as the last drilling cycle, except we're using a G81, which doesn't peck. It just drills straight in and comes out, and because of the G98, it's going to come out to 1 inch above the part and then drill another hole at this dimension in Y. The X doesn't change here. It's on Y0 in the middle of that keyway, so it doesn't need to put an X if it doesn't change. It just comes over in Y from 3/4 of an inch here to -3/4 of an inch. And then of course this is the cancellation of the drilling cycle. Turn the coolant off, come back to home position with the spindle, and then optional stop. And the drill for the tap, which is what all this is the same thing as this up here, except it's using a peck drilling cycle, and it's pecking at every 100,000ths. That's what the Q means in a peck drilling cycle, just like up here the Q is the peck depth. Whatever you put that at, it's going to peck the drill. This drilling peck drilling comes out to the R plane at every peck. A G83 does that. If it was a G73 here, it would just go down 100,000ths, then back up to break the chip, whatever the parameter in the control set to do, and then go back down and keep going 100,000ths, peck, 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 peck. This G83 comes out to the R value, wherever that is. You'll notice this R value on this cycle and this cycle are lower because we're down at the bottom of that keyway making these holes, which is actually 0.250 deep, but this is clearing it by 15 thousandths, just like this was, but this is up at Z0 for this drill. Now this cycle, we are going to have to make a slight edit here, is the tapping cycle for the quarter 20 tap. And okay, we're still using G54, and we're coming over to the first hole where we drilled it, and it's calling up the height offset and moving down to Z1 inch, and it's turning the spindle on. This is a command to turn the spindle on in the forward direction to 800 RPM, but we don't need the MO3 here. The Haas would do the MO3. My Mitsubishi horizontal will give an alarm if you put that MO3 on there in the tapping cycle. The Haas would start the spindle, then stop it, and then tap. So you don't need that. For some reason it did turn the coolant on here, but we're not going to use coolant on the tap. So because this is a tapping cycle, and it's a G84 is a tapping cycle for a right-hand, normal right-hand tap, it would be G74 if it was left-hand. It knows that it's rotating in a certain direction because of the tapping cycle, and you don't need to give it the spindle direction. The controller already knows that, so typically you leave off the MO3 or MO4. This controls it. The G84 is right hand, G74 is a left hand, and it's going to this depth of 850 thousandths, and it's starting to feed at this depth, and the feed rate is 40 inches a minute. Now in this machine it feeds in inches per minute for a tapping cycle, so this feed rate has to match the pitch of the tap and the RPM that you're running it at. So at 800 RPM with a 20 pitch tap, quarter 20 tap, you have to run at 40 inches per minute to match the lead of the tap. Because this machine has rigid tapping, this is what you would do. You pretty much have to do that on this machine, or you probably cross thread the thread. My Mitsubishi horizontal mill, this feed rate is in the lead of the tap, which would be 50 thousandths in this case for quarter 20 tap, and you don't have to worry about the RPM matching the tap's lead, because the lead is the feed. So you just have to, you can put any RPM in here and it'll just feed at whatever the lead you entered. But this Haas mill and most machines, a lot of machines I should say, not all of them, will use inches per minute for this feed rate, so you have to put the right RPM to match, so that when you're turning 800 RPM at 40 inches per minute, the machine is feeding at this 20 pitch or 50 thousandths per revolution. That's what that is. And so then it taps the hole again here at minus 3/4 of an inch, cancels the tapping cycle, turns coolant off if there is, and it comes up to this Z. This is G53 is the machine coordinate system offset, and Z0 would be the zero return position in Z, and then it's coming over to the zero return position in Y to bring the table forward. M30 is the end of the program, rewind to the beginning, and then this percent sign is, like I said, at the end of the program. One thing I'm going to add here, I took the rotation off, is I'm going to add an MOO here to stop the machine right here, so we can put some oil or something on the tap before we tap the holes. It'll just give us time to do that, so we don't have to worry about it. So you'll kind of notice with this program that I'm always coming down. I try to maintain some continuity in the way I program things, and I'm always coming down to 1 inch above the part with every tool before I turn the spindle on here. Now a lot of people don't do it this way. They turn the spindle on when the spindle's way up in the right after it changes to the tool, they'll turn the spindle on as it's coming down, or right before it starts to come down. And that's one way to do it. But with an open machine like this, if there's any coolant on the spindle, you're going to get showered with coolant, or if the coolant turns on up there, you're going to get showered with coolant. That's one disadvantage to that. But the reason I do this mostly is so that if this machine gets any closer than 1 inch to the part and does not try to turn the spindle on for some reason, I know I got a problem with my offset, and I can stop the machine before some accident happens. That's the main reason I do that. If you put a new tool, I mean, this program, it really isn't going to matter too much because we're just running one part here. But if you're running a production job and you change a broken tool or something, and you can let the machine come down to this 1 inch slowly in single block, and it should stop at that 1 inch. You can kind of check it with something 1 inch thick and say, okay, it's at the right place, and then it's going to turn the spindle on. And if you're letting it come down slowly and it gets any closer than 1 inch to the part, you can immediately stop the machine before you have a wreck. So that's the reason I do that. I try to be consistent with that because a lot of times I made programs for other machinists and didn't even run them myself, and they knew that this is the way I programmed, so they knew what to expect when they ran the program the first time. This is pretty important to do if you're doing programming for other people, and they sort of start to recognize your style of programming, and then they know what to expect to happen. So that's the reason I do that. You may have noticed that. So this is the program. Now we're going to upload it to the machine and run the program here. Check that again. It's pretty good. It's maybe a tenth or two bigger than 5/8 of an inch. It's just about right. Okay, we'll run the rest of the program. Do the drill. Use a hex drilling cycle. There's our coolant. spot drill with a tap drill. Quarter 20 tap drill. I got coolant on it. Probably could get away without coolant on the aluminum anyway. We had a program stop for that tap, so I could put some. I'm going to just use WD-40. That's it. Pretty simple machining operation. Next thing we'll do is to lay it down flat and put those two tooling holes in here, and then we can take the vise away and clamp it on the table and profile around, and then bore our holes for the bearings in there. So that's it for right now.